Quadratic programming is the process of solving a quadratic optimization problem. Its objective is quadratic and constraints are linear. Its general form is given as in this equation. The objective is quadratic with equality and inequality constraints. They are linear. The problem can be explained using this figure. This shaded zone is the feasible set. The feasible set is the collection of points where the constraints are satisfied. We have to find a point on the feasible set such that the objective function is minimized. In this figure, apparently this x star will minimize the objective function. So that is the minimizer. Okay, let's begin with equality constrained quadratic programming. We consider only equality constrained. Okay, now we'll try to use the Lagrange multiplier technique. So we define its Lagrangian. This is original objective function along with the Lagrange multiplier. We add this term. It's coming from here. Move this little c to the left hand side. Then cx minus little c equals 0. And we have this term. And the first step is the formulating the primal problem, min-max problem. Minimum over x, maximum over the Lagrange multiplier of the Lagrangian. And its dual problem can be formulated by changing the minimum and maximum. So the maximin is the dual problem. Now we'll first try to minimize the Lagrangian by using a calculus technique. We obtain that the derivative with respect to x of the Lagrangian is 0. Along with this equation, we can find a relationship between x and lambda. Okay, it can be written in this way. That's the first KKT condition. Now we have a second one, the primal feasibility, the original constraint. Okay, we combine them to get this algebraic system. Now ax plus c transpose lambda equal b is this one. Now the bottom one, cx, okay, 0 equals little c, which is this one. So this is the KKT conditions, or the first derivative testers. Let's try to solve this linear system. In order to do that, first we have to make sure this algebraic system is solvable, which means the metric is non-singular. We have to first make sure if the metric is non-singular. We need a little bit of mathematics. Z, the matrix Z, is a metric whose columns span the null space, which means that Z is collection of basis vectors of the null space of C. So Z is a collection of basis vectors. Okay. Now we define here the K, this metric is called the KKT metric. And this similarity transformation with A, Z transpose AZ is called the reduced Hessian. Of course, A itself is the Hessian. Now, this is called the reduce the Hessian. Once the KKT metric K is non-singular, then we can solve the problem and uniquely. So here we have a theorem, existence and uniqueness. We assume two things. One is the full rank for the matrix C. Assume that C has full row rank, and the reduced Hessian is positive definite. So we have two conditions. Then the KKT metric K is non-singular, so that the KKT system admits a unique solution by solving the system. Once it's non-singular, then by inverting this metric, we can get the optimal solution. And the solution must be unique. Okay, this is recall. We rewrite the system here. Now we have some comments. Okay, this KKT system can be solved by using a direct method. However, when the problem size is large, then it'll be quite expensive. So we have to choose some iterative alternatives, and we can apply an iterative algorithm to the entire KKT system, or some special structure of the KKT metric, either part of the KKT metric or after some transforming, particularly the similarity transformation. After that, we try to use some part of the transformed metric. And these techniques are here, the range approach, space approach, and node space approach. And also sometimes people may try to use regular splitting SN relaxation algorithms. And here, the node space iteration is much more popular than the range space iteration. Okay. We'll not deal with the details of iterative or semi-iterative method. Just we'll simply consider some direct solver, and we'll consider a little bit of the iterative algorithm. Okay. Here we have a way to solve the KKT system directly. A direct method to solve the KKT system is to provide a symmetric factorization of the KKT metric. So along with some permutation metric, so it is a transformed metric, and we can get LDL transpose. Here L is lower triangular metric with a diagonal 1. Every diagonal entry is 1. And D is diagonal, but block diagonal. So once we can get such decomposition, then we can solve the problem quite easily. Okay. Now we start with P. For the right side of the KKT system, we multiply P, that permutation metric. And then, now this is the same as, okay, this right side is the same as this left-hand side. Now, K from this one, okay, now P is there, okay, so that now that K is the same as, where is it? Okay, that one, and then PK X transpose. Then now, okay, we multiplied here now P transpose and P, so that this will be identity, so the same. Now, this portion, KP transpose, is replaced by LDL transpose. Right? So we reset this one. Okay, so we now focus on this first term and the last term. We first invert L, so that is this one. So by inverting L for this right side, and this right side, and y1 is this portion. So from here to there will be y1. And then for this y1, we try to invert D, and now inside, after inverting D, that portion will be y2. And again, now L transpose can be inverted to get y3. And here, and so the y3 will be this portion. Now to get x1 lambda, we multiply it P transpose, and we can get that. Right? So once we have this decomposition, then we can get x and lambda, the optimal solution. That's a way of solving the problem along with this LDL decomposition. This LDL decomposition is available in Python. And now if you are using LDL in Python, then the result has the 3 components, 3 matrices, but this one is not L. In fact, it's L0, which is P transpose L. So if we want to get L itself, then you have to multiply this P and to L0, then you can get L. You can see some details from this paper. Okay, we have an example. Consider the quadratic programming for this object function along with this equality constraint. We'll try to express the problem in a metric vector form, and then we'll try to find the KKT system and solve it by using the simple inversion of K. Okay. Here, the object function has this form. Now, from this one, we can get this system. Now, for x1 squared, the coefficient is 4. And also, for x1, x2 term, the coefficient is minus 4. So we put here half and half. And for x2 squared, now the coefficient is 3, so we put over there. Then, now second order terms are considered, and for the linear term, here we have now 4 and minus 2 are the coefficients. And along with this standard form, we can see this matrix is halfway, and that portion is minus b. From the constraint, now 2, 1, 2 and minus 1 is the matrix C, and then right side, C is 1 by 1 matrix. Okay. And now, okay, let's see this formula. This is the KKT system. So we have to put over there A, C transpose, C and 0. Then that is K. And right side is B and C. So we do exactly that way. Now, this portion, okay, that is, okay, this portion is A, and there's a C transpose, large C transpose, and this is a C, and this is a 0, right? And the right side, BC, is now this portion is B, and that is a C. Okay, so we got the algebraic system. Now here we'll try to find the metric vector form of the objective function by here, and by, in a sense, trial error manner, but the metric A can be obtained through derivative. Just if you try to find the Hessian along with derivative right now, okay, let's look at here. This for f, we try to make x1 derivative one more time, and now x1 derivative and x2 derivative. Of course, over there is x1 derivative, and there is x2 derivative, and x2 derivative twice. Then that is Hessian. Once you try to get x1 second derivative, then in fact from this one you'll get 8, which is exactly this one. Now for that one, x1, x2 derivative, once you apply this one, then only the survived term is this one. The coefficient is -4, so that is exactly this one. Of course, this is same. And then, finally, x2 second derivative, then only this one will survive. So the first derivative will be 6, second derivative will be again, the coefficients will be 6, which is this one. In this way, by using the Hessian, the derivative, you can find the metric A. Okay, that is the comment here. Now for the problem, we have A and C, and right side B and little c. Okay, for 3×3 metric. Now first portion, this portion is now A assignment. Now that portion is a C. Now this portion is C transpose. For the right side, now right side here, the B is now in this upper portion, and little c will occupy the bottom of R. Okay, so we finish here in this program, and the system, okay, that is now K, and okay, let's say this whole, the variable, the unknown is better than R. We have that. Okay, now just simply invert K, then we can get the solution. First two components must be X, and the final one will be the Lagrange multiplier lambda. And along with the first two components, we organize the object function half X transpose AX minus X transpose B, then that will be the optimal value, which is 3. Now the solution has a third component, half 0 minus 4. The first two will be the X, and minus 4 will be the Lagrange multiplier lambda. By inverting the KKT metric, we can get the problem. This is a small problem, so you can get it, the solution directly. Okay. Now we'll go to inequality constrained quadratic programming, and I'll try to say a little bit around interior point method. Now the problem is given along with this inequality constraint. Assume A is symmetric, party definite. Okay, then now here exactly the same way, we'll try to introduce the dual formulation, beginning with the Lagrangian, the original quadratic object function, along with now for each, okay, row by row, we try to introduce a Lagrange multiplier mu I, so that we can write down in this way. So this whole thing is the Lagrangian. Of course, this now Lagrange multipliers must be non-negative. Okay. Now again, we are trying to use the dual formulation, and then now minimization of x will be solved first by using the calculus technique, the gradient with respect to x of the Lagrangian can be written in this way. Now this portion is ax minus b, and now from second portion we have d transpose u. So we set it 0 over there. That is exactly this one. And then this is the primal constraint. So there is primal feasibility, and that is dual feasibility. And that is the complementary slackness. For inequality constraint, we needed this one. Now, once we try to solve this system, that is not so much convenient because we have here inequality. So rather than using this inequality, we'll try to make this one equal by adding some quantity non-negative. So we try to add something. So the z is the same as d minus capital dx. But anyway, add something non-negative term such that this inequality equals 0. That's the main idea. Then, now, okay, here, that is dx minus d, dx minus d mu y equals 0. Then again, mu y, zi, multiplication must be 0 by using this one. Now, this equality can be written in this way. And of course, from the beginning, zi must be non-negative. So along with original dual feasibility, under the slack variable, here we have this constraint, and everything else is now equality. So solving this problem is the same as that one, and original one. And to solve this problem, we may try to use so-called the interior point method, and that is along with some central path we'll define soon. Now in some portion, okay, for example, and now this one must be satisfied. Then rather than 0, we'll try to make it slightly larger than 0, and which means that now z is non-zero, and of course mu also positive, again simultaneous positive, then it is non-zero. And we'll try to give some extra term such that now this is positive, then is strictly negative, which means that x is a kind of interior point. So that's the reason it is called. Along with this, some extra term, we can solve the problem more conveniently. Solving this one is more convenient than that one. And again, now the technique is using, again, some interior points. Let's see some mathematical formula here. Now, what we have to solve is this one. Now, f of x mu z is, we collect these terms. Okay, here, this one, and that one, and this one. And we can write in this way. Z is now diagonal matrix of z variables, the select variables. M is now the diagonal matrix of the Lagrangian multipliers. And E is just all one metric. Basically, this is all one metric, all one vector. It's not a metric. Okay. Now, so this is the last term, and we have this one, and if you see original equation, then every is 0. Now, rather than 0, for the last one, we try to give some extra term with now positive tau. Then that means that this is positive. Once it is positive, the last one, that will be positive, which means Z and M are simultaneously positive. From the second one, this is now positive, but whole thing is 0, so that capital D, x minus D, is strictly negative. So that the technique is called the interior point method. Okay, so this the comment is saying this one exactly the same way. Okay, now we have to solve this problem, and from the first derivative we obtained this system. This system, even though we add some extra term, anyway, we have to solve this problem. And solution method is the Newton method. Here, anyway, once this x mu z is satisfying this one, then that is called the central path. So inside the feasibility zone, the feasibility set, and once now this one is becoming smaller, then that will make a path. So that's the reason it is called the central path. So we try to find points on the central path as interior points. Now we try to make practical formulation for the extra term. Now theta is now zi mu I, and averaging them. So after addition divided by p, so it is average the product. And now we put over there theta, and along with some parameter. Okay, in each iteration, these are basically all the way some non-negative. Each one is non-negative. Then we allow, and momentarily, several of them is strictly positive. So that average value will be now non-negative. Once they are 0, then it's done. However, the average value may be positive when some of them is non-zero. So the average value will be positive. Along with the sum of scaling, we try to add this one, and then now try to solve this problem. So by using Newton method, again, we try to get the gradient. So eventually, the gradient of this capital F will be a kind of Hessian of the original objective function. Now, try to here make a gradient, and then the correction vector is negative of the value and some extra term. In this way, we try to find this the correction term. Then once the correction term is found, then from all the iterate, we add the correction term with the scaling parameter. This one is required. Once you try to choose this alpha too large, then probably the solution may be non-feasible, go to non-feasible zone. So try to choose some appropriate alpha such that after this increment, the new iterate will be a feasible solution. In this way, we try to update the x mu and z, and by using the Newton method. So all the way, the points are inside the feasible zone, a feasible set, and along with the the central path, the solution will converge. So that is the idea of interior point method. Okay. Okay, that's the end of the section. Thank you.